All right, so we've talked about singly linked lists before, but what happens when you need to go backwards? That's what we're jumping into today. We're going to demystify the doubly linked list in C++. You know how when you're browsing the web, you can just seamlessly hit the back and forward buttons? Ever stop to wonder how that actually works? I mean, you click back, boom, you're on the last page. Click forward, and you're right back where you started. This is the perfect real-world example of needing to move in two directions. So what's the magic behind that? Well, with a simple singly linked list, you've got a problem. It's basically a one-way street. Think of it like a train on a track that only goes forward. Each little train car, or node, only knows about the car in front of it. So once you pass a station, there's no going back. You'd have to go all the way to the end and start over. Super efficient for moving ahead, sure, but man, is it limiting. And that, my friends, is where the hero of our story comes in, the doubly linked list. This is the awesome solution to that whole one-way street problem. It basically turns our single-track railway into a superhighway where data can zoom in both directions. So let's put them side by side. Your singly linked list, forward only. The doubly linked list, it goes forward and backward. Now, there's always a catch, right? The trade-off here is a little bit of memory. The extra power comes from an extra pointer in every single node, so it's a tiny bit heavier. But honestly, for things where you need to go backwards or delete stuff easily, that extra flexibility is a total game changer. Absolutely worth it.
So what's the secret sauce? It's all about what's inside each node. You've still got your data, and you've still got the pointer to the next node, but here's the magic ingredient, the real game changer, a pointer to the previous node. This little Prev pointer, that's what unlocks the whole two-way street, letting us go backwards just as easily as we go forwards.
Okay, that's enough talk. Theory is great, but let's get our hands dirty and see what this actually looks like in C++. We're going to start at the very beginning with the most fundamental piece of the puzzle, the node itself. So here it is, a super simple C++ class we're calling node. Inside, you've got three things. First, our data, which is just an integer. Then, the two stars of the show, our pointers. Remember, pointers are just variables that hold memory addresses. Next points to the next node in line, and prev, well, that points to the previous one. And when we create a new node using the constructor, we give it some data and set both next and prev to null. That's just our way of saying, hey, this new node isn't connected to anything yet. Super clean, right? Okay, so we've got the blueprint for our node. Now the real fun starts. Let's see how we actually use this thing, how we add new nodes, move through the list, and even take nodes out. This is where we get to see those prev and next pointers do their magic. First up, let's add a new node right at the beginning of the list. We've got this function, insert at beginning. It just needs to know where the list starts, the head, and what data to put in the new node. We'll make a new node, but then we have to be really careful about how we wire up all the pointers to get it in the right spot. Let's walk through it. Okay, step 1, create the new node. Easy. Step 2, tell our new node that its next neighbor is the current head of the list. Now here's the really important part for a doubly linked list. Step 3, we have to turn around and tell the old head, hey, your previous node is now this new guy we just added. See, it's a two-way connection. And for the final step, we just update the main head pointer to point to our new node. And just like that, it's the official new front of the list. All right, so that's the beginning. What about adding a node all the way at the end? The code for insert at end is a little different. You'll see a while loop in there. Why? Well, unlike the head, we don't have a special pointer that just takes us straight to the end. So we have to take a little trip. We have to walk through the entire list, node by node, to find the very last one before we can add our new one. The logic itself is pretty simple, though. First, you create your new node. Then you start at the head and just keep following the next pointers until you hit one that's null. That's your signal. You've found the end of the line, the tail. Once you're there, you just hook up the new node. The old tail's next now points to our new node, and our new node's prev points right back at the old tail. Done. You see, all this careful management of pointers, this is what it's all about. This is what gives the doubly linked list its superpower, the freedom to just cruise up and down the chain of data, no problem. And check this out. Here's that power in action. On the left, we've got print forward. Super simple, right? You just start at the head and follow the next pointers to the end. But look at the right, print backward. This is where the magic happens. We jump to the end of the list, and then we just follow the prev pointers all the way back to the beginning. Try doing that with a singly linked list. You just can't, not efficiently anyway. Okay, so we can add nodes, we can move around, but what about getting rid of them? This piece of code here shows how to delete the node right at the beginning. And this is a really fast operation because we don't have to go searching for anything. We always know exactly where the head is. So how do we pull this off? First, we make a temporary pointer and have it point to the head we want to delete. This is just to hang on to it for a second. Then, we move the official head of the list over to the second node. Now, this new head needs to know it's the front, so we set its prev pointer to null. And finally, we use that temporary pointer we made to delete the old head, freeing up its memory. The list is now one node shorter, but all the connections are still perfectly intact. All right, let's zoom out a bit and see how all of this comes together. We've seen the building blocks, the node, how to insert, how to travel, how to delete. Now let's see them working together in an actual program and tie it all back to those real-world examples. This main function right here is basically the entire life cycle in a nutshell. We start with nothing, an empty list. Then we pop in a few nodes, and then, of course, we print it forwards and backwards just to make sure everything's working. After that, we chop off the first node and print it again to see what happened. It's a perfect little snapshot of how all these functions play together. And I gotta say, this isn't just some boring textbook stuff. Doubly linked lists are everywhere. We already talked about your browser's back and forward buttons, but what about the undo/redo feature in your favorite text editor? Every time you type something, that's a node. When you hit undo, you're just stepping backwards in the list. When you hit redo, you're stepping forward. It's a perfect fit. Same thing for music playlists, right? Skipping to the next or previous song is just traversing a doubly linked list. So let's wrap this up. What are the big takeaways? Number 1, doubly linked lists are all about moving in two directions, forward and backward. Number 2, the magic behind that is the extra Prev pointer in every node. And number 3, the trade-off is simple. You pay a tiny bit more in memory, but what you get back is a huge boost in flexibility. It's powerful stuff. So I'll leave you with a little food for thought. Now that you know how this works, now that you get the power of moving forwards and backwards through data, what apps or software features that you use every single day could be made better with a two-way list? Think about it. The possibilities are pretty cool. Thanks for tuning in.